And welcome to the Rasa Reading Group. Today we are reading a very special paper, a little bit of a special treat. Not that I know ahead of time that I'm going to enjoy this paper, let me put it that way. Not that any of the papers that we read are bad. I try not to choose unpleasant reading material. We are going to be reading the diet paper. So this is actually, I think, the first paper we've read on the reading group that's been by the Rasa team. Hello, Flaviana. Welcome to the stream. Amyan, sorry if I'm saying that incorrectly, is excited. I'm excited too. I'm really looking forward to this one. Okay. So the paper is on diet. So this is the paper where we sort of describe and propose our system. This one is on archive, and I will tell you, we did submit it. The author submitted it. It was not accepted for various reasons, and if I remember, the gist of the reviews were that the reviewers were like, this isn't really a big enough contribution. You know, it's like a multitask learning system that does multiple things, and then it's faster, and okay, so. Which, you know, I can understand if what you're looking for is novelty, but for the people who are using Rasa, like me, I find it to be an excellent contribution. So that's what we're going to be reading about. The paper is Diet, Lightweight Language Understanding for Dialogue Systems, and it's by Tanja, Daksh, Vladimir, who you may know as Vova. He was in the, Vova's been on the office hours a while ago. We talked about research, or maybe he joined me for a reading group. I don't remember, one of the two. And then Alan Nichol. And let's hop right in. Large-scale, pre-trained language models have shown impressive results on language understanding benchmarks like GLUE and SuperGLUE, improving methods considerably over other pre-training methods like distributed representations, GLOVES, and purely supervised approaches. So this is sort of like summarizing history of the field. These big transformer language models are doing well on these benchmarks, as opposed, or better than sort of earlier approaches like word vectors. We introduced the dual intent entity transformer, DIET architecture, and studied the effectiveness of different pre-trained representations on intent and entity prediction, two common dialogue language understanding tasks. So they're going to talk about what the architecture is, and also looking at a couple of different pre-trained representations and seeing how well they work. DIET advances the state-of-the-art on complex, multi-domain NLU datasets and achieves similarly high performance on other simpler datasets. Surprisingly, we show there is no clear benefit to using large pre-trained language models for this task, and in fact, DIET improves on the current state-of-the-art, even in purely supervised setup without any pre-trained embeddings. Our best performing model outperforms fine-tuning BERT and is about 6 times faster to train. So again, just to sort of summarize here, they found that their approach worked better than the transformer language models in addition to being faster and cheaper, which I think is not super surprising given the fact that dialogue is a very specific genre of text, right? So I can't just like take this paragraph and cut it into a bunch of pieces and then put person 1, person 2 in front of it and have it make sense as a conversation, if you get what I'm saying. Whereas my sort of like one-sided dialogue, where I'm talking to you, the audience, thank you for joining, I could sort of like insert the turns that you're taking in the chat, and that would be a dialogue. And I am using language very differently here than I would if I was sitting down to, you know, write a blog post or even to dictate something. So there's pretty strong genre effects, and the big language models, so like BERT, GPT-3, were not specifically trained, T5, all of them, were not specifically trained on dialogue text. The only one that I know off the top of my head that was trained on dialogue text is Convert, and as we mentioned yesterday, that one's no longer publicly available. So also, as I have mentioned before many times in different contexts, you may or may not have heard me say, what gets me excited about a research paper is smaller, faster methods that require less data. So, all right, introduction. Two common approaches to data-driven dialogue modeling are the end-to-end and modular systems. Modular approaches like POMDP-based dialogue policies and hybrid code networks use separate natural language understanding and generation systems. The dialogue policy itself receives the output from the NLU system and chooses the next system action before the NLG system generates a corresponding response. And this is the general way that Rasa works by default, although as of 2.2, we have also added end-to-end learning for specific turns. So if there's an utterance that doesn't fit into an intent, you can add that utterance as raw text into your training data as well. In the end-to-end approach, user input is directly fed into the dialogue policy to predict the next system utterance. Recently, the two approaches have been confined in fusion networks, Mehri et al. 2019. Also, this paper is from 2020, I believe. Early 2020, I want to say? It's been out for a while. In the context of dialogue systems, natural language understanding typically refers to two subtasks, intent classification and entity recognition. Gu et al. Argue that modeling these subtasks separately can suffer from error propagation, and hence a single multitask architecture should benefit from mutual enhancement between the two tasks. Also, in general, in multitask learning, you can see, I won't say always, but often with multitask learning, you can see bigger gains in each of the tasks with the same amount of data, as opposed to using that amount of data to train each of the tasks separately, assuming that the tasks are at least a little bit related. So I remember there was an ACL best paper about, I think it was a combination of video captioning and named entity recognition. Ugh. And this would have been in like 2017, 18, in-ish there, where they were showing that multitask learning worked in this situation. Anyway, it's a good paper. I don't remember who it's by. I remember it was at the ACL in Vancouver, so do with that what you will. Recent work have shown that large pre-trained language models yield the best performance on challenging language understanding benchmarks. See section 2. However, the computational costs of both pre-training and fine-tuning such models is considerable. So this is the sort of green AI paper, which I do recommend you read if you haven't read it. It's a good one. Dialogue systems are not only developed by researchers, but by many thousands of software developers worldwide, like you. Facebook's Messenger platform alone supports hundreds of thousands of third-party conversational assistants. For these applications, it is desirable that models can be trained and iterated upon quickly to fit into a typical software development workflow. Furthermore, since many of these assistants operate in languages other than English, it is important to understand what performance can be achieved without large-scale pre-training. So this is something we've talked about quite a bit. English has a lot of data available for it, a lot of computerized data. Other languages have, in general, much, much, much less. So an example, somebody yesterday was talking about like different Arabic dialects, like Moroccan dialects, I think Sudanese dialect, Moroccan Arabic and Sudanese Arabic, which have far fewer and much smaller corpora available for them than English in particular. Also, my understanding, I don't know a whole bunch about Arabic, hi Chris, welcome back, is that the majority of written Arabic is modern standard Arabic, which is like a more formal form that doesn't have a lot of regional features. So I also imagine the majority of written corpora are probably in modern standard Arabic, but don't quote me. I am not an Arabic researcher by any stretch of the imagination. Yeah. So this sort of section is laying out, hey, here's why we think it's important that a model be smaller and faster to train and require less data. In this paper, we propose DIET, Dual Intent and Entity Transformer, a new multitask architecture for intent classification and entity recognition. One key feature is the ability to incorporate pre-trained word embeddings from language models and combine these with sparse word and character level n-gram features in a plug-and-play fashion, so it's easy to use. Our experiments demonstrate that even without pre-trained embeddings, using only sparse word and character level n-gram features, which you might have for a language that doesn't have a large training corpus available, DIET improves upon the current state of the art on a complex NLU dataset. Moreover, adding Trained word and sentence embeddings from language models further improves the overall accuracy on all tasks. Our best performing model significantly outperforms fine-tuning BERT and is 6 times faster to train. Documented code to reproduce these experiments is available online at Rasa HQ/diet paper. Yeah, Nelson says, too much information is available in English indeed. Yeah. Yup. All right, related work. Also, if you were thinking, hey, Rachel, the goals of this paper seem very aligned to your own sort of like things that you are concerned about in the NLP space, there's a reason I work here, y'all. I think they're doing good work. Yeah, Nelson says, makes developing languages in other languages immense work. Yes, absolutely. Absolutely. And that's, we want to support our developers who are not working in English, like very explicitly. That's something we think about a lot. I know that Vincent in particular has done a lot of work on that. Chris says, written Arabic is the same everywhere, but some dialects are so different that we don't even understand each other. Lebanese versus Tunisian, for example. Interesting. So it sounds a little bit like the situation with Latin in Europe, sort of in the, I don't think they're called the Dark Ages anymore, but when I was in school and learning history were called the Dark Ages, where it was sort of like the language of the scholar class, but then it devolved into like Italian and French and I almost said German, not German, German's not Romance, etc. But there was still this like scholarly form that was the same across regions. It sounds sort of familiar. Hi, Nick. The problem consists in simple things like an effective corpus. Yeah. And yeah, large transformer models just won't work if you don't have a big corpus. All right. Top performing models, Liu et al. 2019, Zhang et al. 2019. I think that's the GPT-2 paper. Don't quote me on that. I don't want to scroll down and then scroll back up, but these are our transformer language models. On language understanding benchmarks like glue and superglue, bigger than regular glue, benefit from using dense representations of words and sentences from large pre-trained models like Elmo, BERT, GPT. Sorry, I'm going to go back and do this. What paper is this? Improving deep neural networks via knowledge distillation for natural language understanding, benchmarking. No, this is a different paper. And then it was, what, Zhang, if I remember? Ernie enhanced language representation with informative entities. Okay, I was deeply wrong about what papers those were. And this is the energy use paper that I recommended. Really good. I do suggest you read it. Anyway, so these are just, I guess, sort of the benchmark leaders when this paper was written. And Nick is recommending that Chris check out Rasa Web Chat and Rasa Chat Room integrations. Nelson says, mine is in Portuguese and we have 2 different branches. Oh yeah, because a lot of languages that were used by nations that colonized the Americas tend to have a version that is used in Europe and a version that's used in the US, and they're fairly different is my understanding. And 5 actually. Interesting. I know a little bit about Portuguese, but it is the language other than English that I know the most about is American Sign Language, which is not super helpful in text-based methods because usually people who know American Sign Language write fluently in English. Yeah. Since these embeddings are trained on large-scale natural language text corpora, they generalize well across tasks and can be transferred as input features to other language understanding tasks with or without fine-tuning. Different fine-tuning strategies have also been proposed for effective transfer learning across tasks. However, Peters et al. Show that fine-tuning a large pre-trained language model like BERT may not be optimal for every downstream task. Moreover, these large-scale language models are slow, expensive to train, and hence not ideal for real-world conversational AI applications. Something about conversational AI in particular is you are talking to a human, so if you have too much lag time, that slows down the pace of the conversation and really can just ruin the user experience. I forget what it was, but somebody was testing a system yesterday and showed the results. And I think it took like 10 seconds per turn for the system to respond, which is quite like a reasonable amount of time to wait for a human who is typing slowly, I guess. But if I'm talking to something that I know is a virtual assistant, I would get impatient. That's all I'm saying. I'm not willing to wait 10 seconds. To achieve a more compact model, Henderson et al. Pre-train a word and sentence level encoder on large-scale conversational corpus from Reddit. This is the convert paper. The resultant sentence-level dense representations, when transferred without fine-tuning to a downstream task of intent classification, perform much better than embeddings from BERT and Elmo. And again, not surprising, these systems are not trained specifically on conversational data. We know that conversations work different than other types of language use. We further investigate this behavior for the task of joint intent classification and entity recognition. We also study the impact of using sparse representations like word-level one-hot encodings and character-level n-grams, along with dense representations transferred from a large pre-trained model. So what we're saying here is, so the dense embeddings are basically each, I don't want to get like too deep into this, but generally dense embeddings are, like a large sparse matrix that's been, compressed down. It is a vector for each word that doesn't have a lot of zeros in it. A sparse representation is a vector for a word that does have a lot of zeros in it. And then one-hot encodings are just like, here's my list of words. Did this word occur? And then a character n-gram. An n-gram is a selection of n items that occur next to each other. So if we were going to break this sentence into character trigrams, the first one would be WE space, the second would be E space A, the third one would be space AL, the fourth one would be LSO, the fifth one would be SO space. So you see chunking up like along a sliding window and then using those as your inputs. And character level methods are particularly good for handling variation in character level input. And I would probably recommend a character level method over a word level method for a language that has a lot of morphology, where like words tend to be made up of multiple bits if you don't have like a morphological toolkit for that language to break the words down into morphemes. So that would be my general recommendation. And character n-grams and one-hot encoding are like, they're fairly old school. I would say that when would they have been introduced? Definitely before I was an undergrad, which was in the aughties. Yeah, but they've been around for a while. I want to say the character n-grams have been around since like the 70s or 80s, but again, don't quote me on that. And having been around for a while, they work pretty well if you have limited compute and limited storage. Nelson said, recently I wanted to train sentiment analysis in Twitter on my own language. Can you guess what the difficulty was? Oh, I guess it would depend on what you were using. It says you're using Orange. I don't think I've used that before. I mean, my guess is that it just wasn't supported. All right, so talking about the sort of current approaches and then the joint multitask learning. So joint intent classification and named entity recognition. In recent years, a number of approaches have been studied for training intent classification and named entity recognition in a multitask setup. Zhang and Wang, 2016, proposed a joint architecture composed of bidirectional gated recurrent units. Oh, that sends me back. 2016, yeah, that's about right. That's when I was in grad school. And bidirectional stuff was like the hotness. That's what everyone was into. The hidden state of each time step is used for entity tagging, and the hidden state of the last time step is used for intent classification. Oh, okay. So it's like stepping over it, like where in the sequence do we care about entities? And then the last step, hey, what was that whole sequence that we just looked at? Liu and Lane, Varkese? I don't know about that one. Et al. And Gu et al. If this isn't Gu, I'm going to feel real bad. Apologies if I mispronounce anyone's names. And if anyone can correct me, please do always feel free to do so. Propose an attention-based bidirectional long short-term memory, there we go, for joint intent classification and NER. Hai Hong et al. 2019 introduce a co-attention network on top of individual intent and entity attention units for mutual information sharing between each task. Co-attention network. I don't think I've run into those before. I don't think we're going to talk about them much, but another potential approach. Co-attention network. Also, transformers, when they were first introduced, some people called attention networks, because the paper was called Attention is All You Need that introduced them. You didn't have any, so for the task of doing sentiment analysis, there were no stop word lists available in the language that they were looking at. Yeah, that's rough. I'm sorry that happened, and yeah. An excellent illustration of why assuming that you're going to have a lot of data and resources for every NLP problem is really Anglocentric. Chen et al. 2019 proposed joint BERT, which is built on top of BERT and is trained in an end-to-end fashion. They use the hidden state of the first special token, CLS, for ident classification. The entity labels are predicted using the final hidden state of other tokens. Okay, so it looks like this is so it's extra layers on top of BERT. And they're using so CLS is a special token that you add to BERT training data that has the classification label for the sequence you're about to input. A hierarchical bottom-up approach was proposed by Van Zo et al. 2019, composed of bi-LSTM units to capture shallower representations of semantic frames. The Berkeley stuff. I work with semantic frames I've never worked with them. I have read about them a little bit. And basically the idea is that they're these sort of am I going to be able to describe this well? They're like a conceptual scaffolding for things that are related. And I think this is the Metaphors to Live Guide by, right? Berkeley FrameNet project. I think it's based on the sort of, originally was based on Lakoff? I think it was Lakoff's work on metaphors. Anyway, this is a body of work I have briefly brushed against. That's all I'm trying to say there. They predict dialogue DACs, intents, and entity labels from representations learned by individual layers stacked in a bottom-up fashion. In this work, we adopt a similar transformer-based multitask setup for diet and also perform an ablation study to observe its effectiveness compared to a single task setup. So the difference between this approach and the previous approaches is the previous transformer approaches, so this BERT one, required pre-training. So BERT is already trained and has a bunch of data. And the, again, I'm not super familiar with co-attention networks, but I'm guessing that that's going to be a different architecture. All right, section 3, diet architecture. A schematic representation of our architecture is illustrated in figure 1. Diet consists of several key parts. Let's look at figure 1. This is the figure that I use in slides a lot, so we'll come back to it. Featurization. Input sentences are treated as sequence of tokens, which can either be words or subwords depending on the featurization pipeline. So there's no expectation here that you're going to be able to break things apart by white space, for example. Another English-centric thing. Following Devlin et al., we add a special classification token, CLS, to the end of each sentence. Each input token is featurized with what we call sparse features and or dense features. We have a whole section about those in the docs if you're interested about using sparse versus dense in Rasa. Sparse features are token-level one-hot encoding and multi-hot encodings of character n-grams for n greater than or equal to 5, so 5 or more characters next to each other. And I believe... Ooh. I'm trying... So that face is... I'm trying to remember the average length of a English word in n-grams, and I believe at a lexicon level, it's between 6 and 7. So the average English word is between 6 and 7 letters. But that includes the morphology within the word, right? So like wolf versus wolves. Wolves is more letters, but it's the same underlying morpheme, if that makes sense. I'm pretty sure it's between 6 and 7, but also this is something I could look up and I'm choosing not to because I'm trying not to get more distracted and sidetracked than I am. Character n-grams contain a lot of redundant information, so to avoid overfitting, we apply dropout to these sparse features, so getting rid of stuff you don't need, basically. Dense features can be any pre-trained word embedding, convert, BERT, or glove. Or, your embedding of choice. Since convert is also trained on as a sentence encoder, when using convert, we set the initial embedding for CLS token as the sentence encoding of the input sentence obtained for convert. I mentioned earlier that these different embeddings are like you are representing a word or a sequence of characters as a vector of numbers, basically. A sentence encoder is doing the exact same thing, except instead of a word that you're representing with a sentence of numbers, you're using a whole sentence and you're representing that as a vector of numbers. Or it doesn't have to be a vector, usually it's a vector. Of the input sentence obtained from convert. Sentence embeddings from convert are 1024 dimensional, and word embeddings are 512 dimensional, so the sentence embeddings are bigger. To overcome this dimension mismatch, we use a simple trick of tiling the word embeddings to an extra 512 dimensions and get 1024 dimensional word embeddings. This keeps the neural architecture the same for different pre-trained embeddings. Tiling. I don't know what they mean by tiling here, but basically all of the input stuff is now the same length as opposed to some of it being a different length, which if you've ever worked in TensorFlow, you've probably gotten dimension mismatch errors. This adds extra contextual information for the complete sentence in addition to information from individual word embeddings. For out-of-the-box pre-trained BERT, we set it to the corresponding output embedding of the BERT CLS token, and for glove, the mean of the embeddings of the tokens in a sentence. So BERT, this has a token in it, so like it's another word, it's a word that a person doesn't say, it's a word that like summarizes the sentence itself. Which I believe they're using for intent here. And in glove, they're just taking, so you have a 512 length embedding for each word. You take the mean of the first row, the mean of the second row, the mean of the third row, and find like the center of all those words in that dimension space. Sparse features are passed through a fully connected layer with shared weights across all sequence steps to match the dimensions of the dense features. The output of the fully connected layer is concatenated with the dense features from the pre-trained model. So these are things like the one-hot encoding, that fully connected layer with shared weights across all sequence steps to match the dimension of the dense features. Okay, so this is reshaping these one-hot encodings to the same shape as the other features so that everything is the same size and you don't get dimension mismatches. Ben says apparently the average length of the English word is 4.7 would explain the n-gram of 5. Is that at a corpus level or a lexicon level? I see that you have a link. Maybe I will. Because there is a interesting pattern where shorter words tend to be used more often, which is probably because words that are very common, words that are very common tend, well, that's not true. I was gonna say words that are very common tend to be shortened. I don't know that that's actually the case. Phonetically, they tend to be reduced, but that's not exactly the same thing. Yeah, by looking at word lengths, Poisson distribution from 80% of 2 and 7, distinct words, counting words regardless, each word only once, remembering how many times it is mentioned. Yes, I was right on the money. So I've just followed the link that Ben shared. And if you count the number of words in a corpus, and you just like, you counted sparse every time it showed up and features every time it showed up, that's where you'd get the 4-ish number. And if you count sparse and features only once each because they are distinct words and you only count each distinct word, then you get around 7.6. So the difference between including usage data and not including usage data. Oh, nope. That's not what I meant to do. Including usage and not including usage in the form of normalizing by corpus counts. Yeah. Sorry. No, I'm still thinking about the more common words being shorter. I'm sure there's some like baloney Evo Psych solution, suggestion about why that is. And if I learn about it, it's just going to make me angry. So I'm not going to dig into that anymore. But thank you for looking that up, Ben. Sitting weird. Transformer. To encode context across a complete sentence, we use a 2-layer transformer, Vaswani et al., with relative position attention, Shaw et al. So not using the... Vaswani has like a really weird a positional attention mechanism that to this day is like the weirdest part of that paper for me. So they're using a different positional attention mechanism. Because transformers don't care about order, right? Every token looks equally at every other token, and then attention determines the amount of weight it's given. It's not really weight, but you know what I mean. The transformer architecture requires its input to be the same dimension as the transformer layers. Therefore, the concatenated features are passed through another fully connected layer with shared weights across all sequence steps to match the dimension of the transformer layers, which in our experiments is 256. So this is just describing like how they got everything to be the same size. Named entity recognition. A sequence of entity labels, Y entity, is predicted through a conditional random field, CRF, 2001. 2001? Was it that late? I could have sworn CRFs were older. Tagging a layer on top of the transformer output sequence alpha, corresponding to the input sequence of tokens. So LE, so the likelihood of an entity is the negative log likelihood for the CRF given the input tokens and a specific entity. So you have a list of entities you know about, and you assign each of them a likelihood given this input. Oh. All right, time to read more math. Intent classification. The transformer output for CLS token, alpha CLS, and intent label, Y intent, are embedded in a single semantic vector space. HCLS is, oh god, all right, so we have there's no way that says real numbers to the 20th power, right? Okay, so we have H, which is drawn from the set of... I could have sworn that fancy R meant real numbers. And to the 20th? Okay, so there's a set of thing, and for each of them... No, all of these things have to come from this. Yeah? Yeah? feel free to hop in at any point, audience. Okay, so we've got all of our tokens for each of the, oh, I see. Okay, so the HCLS comes from each of these alpha CLS, where alpha is the input sequence, and then the intent comes from all of these intent labels. Okay, and then they're embedded in the same space. Okay, that makes sense. So using something like star space or some sort of multi-thing embedding. We use the dot product loss to maximize the similarity. S plus I. Oh, okay. With the target label, Y intent plus, and minimize similarities with negative samples. Okay, so they're just trying to move, the thing that they're looking at closer to the thing that it is and farther away from the things that it isn't. That makes sense. And then this is how they're doing it. Where the sum is taken over the set of negative samples, omega negative sub I, and the average is taken over all examples. At inference time, the dot product similarity serves as a ranker over all possible intent labels. Okay, so we have, during training, we have a labeled example. We're trying to move it towards, in this embedding space, the correct label and away from the incorrect labels, and then you're doing that multiple times. And then at inference time, you look at all the intent labels, you look at your input, and you're like, hey, which of these is the most similar in the embedding space given our training data? Chris says it means that H is a vector of 20 real numbers. That makes a lot more sense. Okay. Yeah. Okay, so the we've got sort of 20 dimensions for the tokens, and then for the intents, and then we're projecting those into the same space. Helpful. Thank you. I have a poor friend who was a math PhD student, and halfway through was like, nah, I don't want to. But when I was first starting in machine learning, I used to send him a lot of like pictures of stuff and be like, what the hell does this mean? What is this symbol? I don't even know how to Google the name of this symbol. Hot tip, if you are in Google Docs, you can add a symbol and then draw the symbol, and then it'll bring up like a series of like all the Unicode matches for the thing that you drew. So if you are genuinely stuck on what a symbol is in math, that is my recommendation for how to look it up. Masking. Inspired by the masked language modeling task, Taylor 1953, Devlin et al. 2019. I think the Taylor task is the original close task, which was, it's a fill in the blank, right? If you've, depending on your experience with an educational system, you may have encountered that in school. We add an additional training objective to predict randomly masked input tokens. We select at random 15% of the input tokens in a sequence. For a selected token, in 70% of cases, we substitute the input with a vector corresponding to the special mask token mask. In 10% of the cases, we substitute the input with the vector corresponding to a random token, and in the remaining 20%, we keep the original input. The output of the transformer, alpha mask, for each selected Y token is fed through a dot product loss, similar to the intent loss. There's a dot product loss. Where SM, they're trying to maximize the similarity between the mask token and the actual token that was replaced, is the similarity with the target label token. And they're trying to increase the distance, or maximize the distance, move away from the tokens that it is not. And they can do this because they have labeled data, and then during inference time, it's like, hey, what's closest given your training over time? Are the corresponding embedding vectors, which are real numbers of length 20. Thank you, Chris. The sum is taken over the set of negative samples, and the average is taken over all examples. We hypothesize that adding a training objective for reconstructing masked input should act act as a regularizer, as well as help the model learn more general features from text, and not only discriminative features for classification. So one of the problems with a lot of the transformer language models is that they can be, for a specific task, very reliant on specific words. So like not, for example, and being able to sort of like make that a little bit fuzzier in the training data. Like sometimes it's not, sometimes it's a different word, sometimes it's just missing. They're arguing here should help those situations. Ben says we have random replacement in the masking. Yes. And I want to say that's also proposed in the original BERT paper, but it has been a couple years since I read that. But yeah, I believe there is some replacement in the BERT paper as well. Or at least I have seen people do it. I don't remember if it's in the original BERT paper or not. Total loss. We train the model in a multitask fashion by minimizing the total loss. So the loss for the intents, the loss for the entities, and the mask loss. Okay, so the masking is the third loss. Yeah. And if we go up here, you can see here we have the mask loss, so that's sort of like the fill in the blank. Can you guess that correctly? We have the intent loss, where we're looking like, hey, how close to our actual intent is the intent that we identified? And then we have the entity loss. Hey, did we correctly identify these entities in this text string? Actually, at this point, it's not the text string. At this point, it's the CRF. So it's multitask. The output that we're interested in is actually two tasks, the intent and the entity, but we're also using the third task mask as a regularizer to help avoid overfitting, basically. The architecture can be configured to turn off any of the losses in the sum above. So if you don't think the mask loss is going to be reasonable, you can just get rid of it. Batching. We used a balanced batching strategy to mitigate class imbalance, as some intents can be more frequent than others. Understatement. We also increase our batch size throughout training as another source of regularization. Experimental evaluation. In this section, we first describe the data sets used in our experiments, then we describe the experimental setup, followed by an ablation study to understand the effectiveness of each component of the architecture. And I'm not going to go too deeply into like this because it's basically what we just said. But sort of peeking ahead, some of the things that they're going to work on or talk about is getting rid of the pre-trained embeddings. So there's only the sparse features in the feed forward for the input words. And probably other stuff. That's the one that I remember from the abstract that I was like, yeah, that sounds helpful. And also here for the masking, getting rid of the pre-trained embeddings as well. Yes. Scroll. Also, Vincent has a video on diet where he goes over this in a lot more, sort of like talking about each of the components in turn. So I don't feel like we need to do that twice. Datasets. We use 3 datasets for our evaluation: NLU benchmark, ATIS, and SNPs. ATIS. The focus of our experiments is the NLU benchmark dataset, since it is the most challenging of the 3. The state of the art on ATIS, and SNPs is already close to 100% test set accuracy, see table 5. So it looks like folks are pretty much at ceiling on this task already. NLU benchmark dataset. The NLU benchmark dataset, Leo et al. 2019, available online. I imagine that's a link. Sure is annotated with scenarios, actions, and entities. For example, schedule a call with Lisa on Monday morning is annotated with the scenario, calendar, the action, set event, and the entity's event name, a call with Lisa, and date, Monday morning. Did we read this paper? This sounds very familiar. I may or may not have read this paper. I'm going to assume I didn't. The intent label is obtained by concatenating the scenario and action labels, e.g. calendar, set event. Okay. The dataset has 25,000 utterances, which cover multiple home assistant tasks, such as playing music or calendar queries, chit-chat, and commands issued to a robot. So speaking of imbalanced tasks, I think something like 80% of requests to Home Assistants are to set a timer. And like the following, like the majority of the rest of them are like checking time or weather and then playing music. There's been a bunch of work done on that. But the upshot of that is that of all of the intents that a Home Assistant can handle, most of them are probably not going to be used by most people most of the time. The data is split into 10 folds. Each fold has its own train and test set of respectively 9K and 1K utterances. Overall, 64 intents and 54 intent types are present. Excuse me. ATIS, Hempel et al. 1990, is a well-studied data set in the field of NLU. That is a venerable data set. It comprises, I say that, I've definitely worked on Switchboard, which I think is older. It comprises annotated transcript of audio recording of people making flight reservations. We use the same data split as Chen et al., originally proposed by Gu et al. And available online. The training, development, and test sets contain so many utterances. The training data set has fewer intents and more entities. Yeah, so this one is would probably be a little bit more difficult to pick the entities out. Although in general, detecting entities is a little bit of an easier problem. SNPs. This data set is connected from the SNPs personal voice assistant. I don't know that I've ever heard of it. Maybe I have and I forgot. That's also very possible. It contains 13K training and 700 test examples. Wow, that's a split. Okay, so they're using the same split as somebody else. Sorry, what I'm just saying there is that is a very small test example set given the training examples. So they're using somebody else's data set, split 700. Examples from training set are used as development set. The data can be found online. The SNPs data contains 7 intents and 39 entities. Okay, so this is a even smaller data set. Experimental setup. Our model is implemented in TensorFlow. We use the first fold of the NLU benchmark dataset to select hyperparameters. We randomly took 250 utterances from the training set as a development set for that purpose. We trained our model over 200 epochs on a machine with 4 CPUs, blah, blah, blah. We use ADA for optimization, learning rate. I'm guessing this is going to change over time. That's right, because Adam does. The batch size, it was increased incrementally, blah, blah, blah. Training our model on the first folds took about 1 hour. Oh, that's not bad. Training our model on the first fold of the NLU benchmark takes 1 hour. At inference time, we need around 80 milliseconds to process 1 inference. I'm trying to snap. It's not very effective. Yeah, how big was the... It was big, right? Each fold, yeah, so it's about 10K training examples, which is not bad, especially because it's doing, 3 tasks. And then that inference time is pretty good, I would say. Yeah. The NLU benchmark data contains 10 folds, each with a separate train and test set. To obtain the overall performance of our model on this data set, we follow the approach of Vanzo et al., train 10 models independently, 1 for each fold, and take the average over the final score. And if each model is only training for, an hour on 1K80, which is not, even when this paper was written, was not the best possible GPU is what I'm trying to say there. I was trying to come up with a car metaphor, and I was like, Cadillac. The Cadillac of GPUs. I don't know if Cadillacs are... I don't know what the expectation of what a Cadillac should be maps well there. Anyway, what I'm saying is training that model 10 times is like a fair amount of compute, but like not that much, especially compared to something like BERT. Even fine-tuning BERT. Microaverage, precision, recall, and F1 scores are used as metrics. True positives, and false negatives for intent labels are calculated as in any other multi-class classification task. An entity counts as true positive if there is an overlap between the predicted and the goal to span and their labels match. Okay, so it would still count even if like it cut off the first, even if there was only one letter worth of overlap, and the label was correct. So Table 1 shows the results of our best performing model on the NLU benchmark dataset. Our best performing model uses sparse features, so the best performing model will be dependent on the hyperparameter tuning that they did earlier. Our best performing model uses sparse features, i.e. one hot encodings at the token level and multi-hot encodings of character n-grams n less than or equal to 5. These sparse features are combined with dense embeddings from convert. Our best performing model does not use a mask loss. Interesting. We outperformed Hermit on intents by over 2% absolute. Blah, 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 blah. They're just talking about them versus a different model. I don't know. Maybe I shouldn't skim over that, but I'm just going to look at the table, which has the same information anyway. So this is their model, sparse features for both words and n-grams, as well as the convert embeddings, which were based on conversational data. And they do better by, I'd say a fair amount. And then, oh, I see. This is table 1. I was trying to like carry this across and I was deeply, deeply confused. Table 1, results from Hermit for our best performing configuration of diet and the NLU benchmark dataset. Our best performing model uses word and character levels, sparse features, and combines them with embeddings from convert. The model does not use a mask loss, which is interesting. Interesting that the mask loss did not actually help that much. I imagine the degree to which the mask loss will be helpful is dependent on the specific intents you're looking at. And if there's things where intents are likely to be different by one word, I think a mask loss is going to be very effective in picking that apart, would be my guess. But I mean, that's an open question. That's a research question. Yeah, interesting. And then this is when it's trained on just a single task. Interesting. And is this on the same benchmark dataset? It is. Interesting. So it does worse at entities, but so I'm comparing this and this. So it does worse at entities and very slightly better with lower variance on intents. Interesting. If it's used on one task at a time instead of doing multitask learning. So it looks like the big improvement, which is, I will say, much bigger, right? This is like, I don't know, 0.7? Don't make me do that. So this is like a 0.7 increase, and also this variance is wider. So, but here, like the difference between adding the multitask learning to the improvement on the entities is pretty large, I would say. So the main benefit of the multitask learning here is really in improving entity identification, which makes sense because the entities that you talk about are not independent of the intents that you are uttering, right? The domain that you're talking about or the specific thing that you want to do. So being able to handle them at the same time in the same embedding space, I think makes sense. But at the same time, you can talk about an entity without bringing up a certain intent. Sorry, you can talk about an intent without bringing up a certain entity. So I think that there is, thinking about it, there is like a, the probability of an entity is conditioned on the intent. The probability of the intent is, it's probably correlated, but I don't know that it's conditioned on the entity. I imagine they'll talk about that a little bit further down. They evaluate different components of the model architecture as it covers multiple domains and has the most number of intents and entities of the 3 datasets. So the importance of in-joint training. Yulong says, since BERT is trained on monologic texts, so not dialogues, it's a little weird to me that they use BERT embeddings and compare BERT baselines and evaluate on dialogue NLU tasks. Yeah, and I think that's part of the point of this paper, right? And I will say that the embeddings that they were using for this particular example are from Convert rather than BERT. Yeah, so the model that's being evaluated here, the Rasa model, is based on these Convert embeddings, which are like BERT, but are trained on dialogic text from dialogues. And point of the paper is that, like, hey, it's not surprising that we're doing better than with BERT, because it's not, it's not a dialogue, right? But there are definitely other researchers who have used it and have included it in their work, so I think it's good to discuss. Yeah, I think that's a great point, Yulong. Okay, and then they talk about the single tasks. The results show that performance of intent classification slightly decreases. It should be noted that the best performing configuration for single task training for intent classification corresponds to using embeddings from Convert with no transformer layers. So Convert is this dialogue trained BERT-like model. However, the micro-average F1 score of entities drops from 86% to 82% when entities are trained separately. Inspecting the NLU benchmark dataset, this is likely due to a strong correlation between particular intents and the presence of specific entities. Yeah. For example, almost every utterance that belongs to the play game intent has the entity game name. Also, the entity game name only occurs together with the intent play game. We believe that this result further brings out the importance of having a modular and configurable architecture like Diet in order to handle trade-off in performance across tasks. Yeah, so if you are building an assistant and you care much more about intent identification than entity recognition, then it might make sense for you to train things independently. But if for you, entities are much more important than intents, then it makes sense to make sure that, you're training jointly to get the boost to entities. All right. How much time do we get? Oh, we're close. Okay, I think we can finish the paper today. And then I'll be quiet for a while, because I don't know if you can tell, my voice is getting a little rough. Importance of different featurization components and masking. As described in section 3, embeddings from different pre-trained language models can be used as dense features. We trained multiple variants to study the effectiveness of each, only sparse features, i.e. one-hot encoding at the token level and multi-hot encoding of character engrams, and combinations of those together with Convert, BERT, or Glove. Additionally, we trained each combination with and without the mask loss. The results shown in Table 3 show F1 scores for both intent classification and entity recognition and indicate multiple observations. Diet performance is competitive when using sparse features together with the mask loss without any pre-trained embeddings. So if you are working in a language other than English and you don't have good pre-trained embeddings, Diet should work for you. Adding a mask loss improves performance by about 1% absolute on both entities and intents. Diet with Glove embeddings is also equally competitive and is further enhanced on both intents and entities when used in combination with sparse features and mask loss. And Glove embeddings they've been around for a while. I want to say there are some multilingual ones, but primarily they were developed in English. We hypothesize, interestingly, using contextual BERT embeddings as dense featurizers performs worse than Glove. We hypothesize that this is because BERT is pre-trained primarily on prose and hence requires fine-tuning before being transferred to a dialogue task. The performance of Diet with Convert embeddings support this, since Convert was trained specifically on conversational data. Convert embeddings with the addition of sparse features achieves the best F1 score on intent classification, and it outperforms the state of the art on both intent classification and entity recognition by a considerable margin of around 3%. Adding a mask loss seems to slightly hurt the performance when used with BERT and Convert as dense featurizers. Interesting. I don't have a good hypothesis as to why that could be. Comparison with fine-tuned BERT. Sip of coffee. Following Peters et al., we evaluate the effectiveness of incorporating BERT inside the featurization pipeline of diet and fine-tuning the entire model. Table 4 shows diet with frozen convert embeddings as dense features and word character level sparse features. Table 4 shows diet with frozen convert embeddings as dense features and word character level sparse features outperforms fine-tuned BERT on entity recognition while performing on par for intent classification. The result is especially important because fine-tuning BERT inside diet on all 10 folds of the NLU benchmark dataset takes 60 hours, compared to 10 hours for diet with embeddings from convert and sparse feature. And if you're only doing it on one fold, which I think is more, a better proxy for what you're probably gonna be using if you're getting started with your first assistant, that takes 1 hour. Yulong says, I meant the later part, they compare BERT fine-tuning instead of dialogue pre-trained models, e.g. Dialogue GPT, TOB BERT, so I'm curious how they perform on that tasks. I'm gonna quickly look up Dialogue GPT. I believe that came out after this paper. I'm just searching that in another window over here. Microsoft, obtained yesterday, the archive paper. Okay, so this one is, came out November 2019, was revised May 2020, and this one, April 2020 was when it was submitted, and then revised at the same time. Yeah, that's a good question. Hugging face, blah, 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 show conversational. Pre-trained model are publicly released. Yeah, I don't know when it was actually released. And also, I don't know about the choice to do that. Yeah, it could possibly do better. I would say Convert in particular is a transformer BERT-like model, so I think it is playing that role in this paper. But yeah, yeah, I think that could be a good benchmarking paper if that was something you were interested in writing. It doesn't have to be a paper. I would actually probably be a pretty good blog post. I'd be interested in that as well. Yeah, so did not do as well when using BERT specifically, and also just took, so much longer. So much longer. Experiments on ATIS and SNPs. In order to compare our results to the results presented in Chen et al., we use the same evaluation method as these other papers. They report the accuracy for intent classification and micro-averaged F1 score for entity recognition. Again, true positives, false positives, and false negatives for intent labels are obtained as for any multi-class classification tasks, and they're doing that span thing. All experiments were run 5 times. We take the average over the results for the final numbers instead of cherry picking and taking the best result. To understand how transferable the hyperparameters of diet are, we took the best performing model configurations of diet on the NLU benchmark dataset and evaluated them on ATIS and SNPs, so no further hyperparameter tuning. The intent classification accuracy are all in Table 5. Due to stricter evaluation method, we tagged our data using the BAILU tagging schema. The use of the BAILU tagging schema is indicated by the star in Table 5. I'm not familiar with this. Remarkably, using only sparse features and no pre-trained embeddings whatsoever, diet achieves performance within 1 to 2% of the joint BERT model. Using the hyperparameter, which is a dialogue-specific model. Using the hyperparameters from the best performing model on the NLU benchmark dataset, diet achieves results competitive with joint BERT on both ATIS and SNPs. So let's see if we can find... there's a lot of tables we haven't looked at also. Yeah, we've got 3 tables. So let's look at them really quick. So here are the different ablation studies. So basically you take various stuff out of your model and you see what you actually need and what you don't need. So here are the results with no dense features, which are honestly not that bad, all things considered. And then results with the glove features. Although it does look like if you're using no dense features, adding the mask loss does help a little bit. So good to know there. All of the glove stuff with and without sparse features, all the BERT stuff with and without sparse features. And the best performing are Convert, which is this conversational BERT-like model. I think we've read the paper in the reading group before, without mask loss. And for entities, it does better if you don't use sparse features. And for intent, it does better if you do use sparse features. Yeah, so that is the results there. And then this one, Table 4, comparison of best performing feature set from diet against a fine-tuned tunable BERT inside diet on the NLU benchmark data set. So comparing, again, sparse features and convert to BERT seems to be doing better overall. Although the precision on entities, I think also that was the pattern with the Hermit model as well. So interesting to note that. And this is joint BERT, which was, like Yulong was mentioning, this is a, one of a similar model. So it's BERT, and then it's trained specifically on a dialogue task, or fine-tuned, not trained, I should say, and then compared to the various configurations of the diet model. And I will say, it doesn't, doesn't get quite the same numbers, but it is 6 times faster to train. And particularly because our sort of approach that we recommend is if you've heard about conversation-driven development, it's something that we talk about a lot. The approach that we recommend is that once your system is interacting with humans, you go through, you annotate those conversations, you annotate the entities, you correct them, you add training data, and you retrain. So because that's what we're proposing, this sort of CI/CD model of AI systems where you are retraining constantly, the improvement in training time in particular will have compounding effects if you're using that development model, which I think is a good development model, right? I recommend you use it. So I would definitely save 59 hours of training time every week, or however often you retrain your model versus 1 point of performance. So and that's a decision for you to make in your application to the degree to which that is important to you, but certainly to me and other people not made out of money without just armfuls of GPUs and servers, I think it does make sense to consider that. Also, the inference time is much faster, so you don't get that lag in having conversations. All right, conclusion. We introduced Diet, a flexible architecture for entity and intent modeling. We study its performance on multiple datasets and showed that Diet advances the state-of-the-art on the challenging NLU benchmark dataset. Furthermore, we extensively studied the effectiveness of using embeddings from various pre-training methods. We find that there is no single set of embeddings which is always best across different datasets, highlighting the importance of a modular architecture. Yeah, and I would say, also, this is flexibility on the architecture side, but also having an architecture that can handle flexibility on the data input side. Furthermore, we show that word embeddings from distributional models like GloVe are competitive with embeddings from large-scale language models, and that, in fact, without using any pre-trained embeddings, Diet can still achieve competitive performance, outperforming state-of-the-art on NLU benchmark. Finally, we also show that the best set of pre-trained embeddings for Diet on NLU benchmark outperforms fine-tuning BERT inside Diet and is 6 times faster to train. So, and then, citations. So the big takeaway here is that this approach, you can turn off and on bits as you need for your particular use case. So you can, if you remove the arrows around total loss, come on, center. There we go. So if you remove the arrows around total loss, you can train the entities and the intents separately, which might be helpful, particularly if you really care about intents more than entities. You can remove this mask loss, which might be helpful if you're using dense embeddings. You can remove these pre-trained dense embeddings. So because it's so modular, you can just pop out the bits that aren't helpful for you, or that you don't care about, or that you just don't have, right? And improve your system performance, or at least not suffer a big loss to system performance and gain an improvement in training time. Yeah. Oh, thank you. These are Ojibwe strawberries from an artist who I used to have the name of on my desk, but I really like them. Yeah, so I'd say the overall takeaway is that diet's good and you should use it. If you are in Rasa, so a change that we have made as of 2.0 is that when you train your first model, we use diet by default. I believe that is for English models specifically. But yeah, so it should be very easy to take a diet model or modify a diet model and then plug it into the Rasa system, and we, it works well and it's fast. So we've sort of included it by default in configs for Rasa systems when you start a new one. So if you've used Rasa since 2.0, you've already used it magically. Yeah. Thank you for joining, everybody. I think that's about all I have to say about diet, and my voice is letting me know that it's about time to stop speaking quite so much. So thank you for joining today. I hope you enjoyed this. I don't know what we'll read next week. It'll be something fun. And tomorrow we're going to be talking about actually character level models a little bit. And in live coding, we'll be talking about spelling variation and typos and misspellings and that sort of stuff and how to handle them. Which not super helpful with pre-trained embeddings, but with character level n-grams, you can handle them very well. So we will handle that tomorrow, and then we'll be back on next Wednesday with our next office hours with, I believe, Tom or Tobias. And whichever one it's not will be here next week after that on the 24th. Also, I was wrong. I said that I wrote it down wrong. I said that the launch notes live stream was going to be today, and it was definitely on the 18th, and I was absolutely wrong about the date. I'm so sorry. I think that the YouTube post was correct. So, mea culpa, I'm sorry if you got up early or stayed up late to watch that. It's going to be next week, so tune in for that. And yeah, I'll see you tomorrow. Otherwise, have a great weekend, and I'll see you next week.